Hello everybody. In today's session, before solving some problems on transformers, I like to continue with the last topic. Okay? It is called voltage regulation of a transformer. Now the transformer will be connected to a supply and it will be supplying a load. There are two conditions for the transformer what you get. Generally, if there is no load connected on the secondary terminals, I call the transformer is on open circuit or under no load condition. No load condition means the secondary is not connected to any power consuming network, therefore secondary winding will not carry any current. So under this situation, even the primary current or the current drawn by the transformer from the supply in the primary winding will also be smaller. So the function of this current, what is there in the primary winding under no load condition, is to produce the no load losses as well as to set up the magnetic field in the core of the transformer. Under this condition, the primary winding will have an induced EMF and the secondary winding also will have an induced EMF, but there is no current in the secondary winding. So hence there is no current. The impedance of the secondary winding will not carry any current, therefore there won't be any voltage drop. So that in this condition, the induced voltage in the secondary winding and the terminal voltage at the secondary winding terminals both will be same. Now suppose say if under this condition a small amount of load is added to the secondary terminals. So now this induced voltage in the secondary winding will give you a current to the load. So as there is a current in the secondary winding, the primary also draws certain higher value of the current from the supply. This is to supply the energy what you have transfer from primary to secondary. So that primary will draw more current. Now if you consider the secondary winding, now since there is a current in the secondary winding, there will be a small voltage drop in the impedance of the secondary winding. So because of this impedance drop, the voltage what is available at the terminals of the secondary winding will be lesser than the induced EMF in the secondary winding. Now if I consider the two voltages, the induced EMF in the secondary winding can be represented by E2, what I am given here, E2, and the terminal voltage will be represented by V2. So under load condition, there will be always a difference of between the induced voltage E2 and the secondary voltage terminal voltage V2. The difference what you have, we call it as the voltage drop in the secondary winding given by I2Z2. Now the load on the transformer can continuously increase. We can increase the load. As you keep on increase the load, the current in that secondary winding also increases. So this causes the primary to draw a higher current. So the current drawn by the primary winding from the supply also increases. So this increase in the windings will cause an increased amount of voltage drops in the windings. That means the I2Z2 what I have, it will keep on increase with the increase in the current. This I2Z2, what we call it as voltage drop in the secondary winding, Z2 is constant. Z2 will have two parts. It is the resistance. Okay, one part is because of the resistance of the secondary winding, and the other part what we call it as reactance, okay, inductive reactance. It is because of the leakage flux linkages, okay, in the secondary winding. This leakage flux linkages will causes an inductance, and that inductance, because the transformer is connected to an AC circuit, will get converted to reactance. So the combined effect of resistance and reactance, we call it as impedance. So this impedance drop is not constant for a transformer, it keep on changing with the load. Now as you consider this load on the transformer, there will be a condition where the current drawn by the or current given by the secondary winding to the load will be equal to the rated value. So for example, I have a transformer which is rated to 1000 volt amperes, 1000 volt amperes. Let us say this transformer is rated to a 230 volts at the secondary, okay. So I can write the transformer rating as V2 I2 is equals to 1000 amperes. Therefore, I2 will be equals to 1000 divided by 230. I will be getting somewhere around 4.7 amperes. So, this is the maximum current what the transformer will carry depending upon rating. So, when the transformer is supplying 4.7 amperes, this transformer which is rated to 1000 volt amperes, okay, not 1000 amperes, it should be 1000 volt amperes, I say it will be under full load condition. Now, the voltage drop what you have under the full load condition, okay, will be given by E2, the induced voltage in the secondary winding, and V2, the voltage what I can measure when the transformer is supplying full load at the secondary terminals. So, this difference when you express as a percentage of full load terminal voltage, I call it as voltage regulation. Okay. This is a very important property for the transformer. All transformers should have a very low value of voltage regulation. So, when the voltage regulation is a very low value, we say the transformer operation will be better. Okay. So, this slide says at this loading condition, the voltage between secondary terminal is V2, okay, across load terminals, which will be less than the no load secondary voltage. Okay. Under no load condition, there won't be any current in the secondary, therefore I2 Z2 will not be there, it is 0. So, such condition your V2 will be equal to V2. Under load condition, there will be a drop in the impedance of the secondary winding, therefore E2 minus V2 will give you this V2. Therefore, this V2 under load condition will be definitely lesser than E2, the induced voltage in the secondary winding. Now, this voltage regulation what you have will generally be calculated under full load condition. Okay. Now, the definition of regulation, it will be like this. Now, let us say the transformer, I have a transformer, okay. I am not showing the secondary winding, I am just showing not showing the primary winding, I will be just showing the secondary winding here. This is the impedance of the transformer. E2 is the voltage induced. So, this is giving us a current of I2 in the secondary, there is an impedance connected here, Z2. R2, this is the leakage reactance for the transformer. So, the combined effect of these two, I will call it as Z2. I have a loop here for which I can apply Kirchhoff's voltage law, then I will be getting E2 is equals to V2 plus I2 Z2 as per the Kirchhoff's voltage law. Okay. Now, you can see E2 minus V2 what we have will be I2 Z2. I will take a no load condition, okay, which say let us say full load condition. Full load condition, if I consider, under this condition the current is much larger, okay, equal to the rated current. Therefore, this V2 what you have will be less than E2 because of this term. Okay. I can write V2 is equal to E2 minus I2 Z2. Therefore, I can say under full load condition V2 will be less than E2. Now, let us say suddenly I reduced the current to 0. What do you mean by that? Means I remove the load all of a sudden. Such condition I2 becomes 0, therefore I2 Z2 also becomes 0. Okay. So, from this equation when I2 Z2 becomes 0, the terminal voltage, secondary terminal voltage V2, it jumps to a voltage of V2. Under no load condition, you can see the voltage is rising from V2 to E2, and under full load condition V2 will be less than E2. So, this voltage rise what you have, okay, expressed as percentage of full load terminal voltage with or keeping the primary voltage a constant, okay, is called as voltage regulation. Okay. Exact definition for this voltage regulation is like this: the raise in the terminal voltage, okay, from full load to no load, when the full load at a specified power factor suddenly thrown off, keeping the primary voltage a constant. So, this is the exact definition for the regulation of a transformer. Now, why we have to say the power factor? Okay, I have not mentioned anything about the power factor here, I just simply said the load impedance. This should be ZL, the load impedance I said. Okay. So, that impedance here can be like this, R plus JXL, or I can also have R minus JXC. When you have R plus JXL, I call it as a inductive load, R minus JXC, I call it as a capacitive load. Most of the loads are inductive, okay, and the voltage drop what you have actually also depends upon the power factor of the load, that is the cosine of the angle between the voltage V2 and the current I2. I have just given this equation saying that these are all voltage drops. Strictly speaking, all these voltages what all we have, they are vectors. So, I should consider with magnitude and also angle while calculating the raise in the voltage. Okay. Now, the raise in the voltage here for a given load, it depends on the power factor. That is why we say the full load at a specified power factor is suddenly thrown off. In the end of the statement, I also said primary voltage being constant. Why? Because means the voltage what I am giving to the primary winding, depending on that I will have a induced voltage in the primary winding. Now, the induced voltage in the secondary winding what you have E2 here, it depends on the primary voltage. We saw while deriving the transformation ratio, K is equals to, we took it as E2 divided by E1. So, from this relationship E2 depends on E1 through K1, and this E1 depends upon the supply voltage, because the flux which is responsible for the induction of this, say getting this voltage E1 induced in the primary winding, it depends on the supply voltage. Therefore, the supply voltage or the primary voltage what you are giving, that should be kept constant while calculating the regulation for the transformer. So, this is the about voltage regulation. So, let us see some problems on the transformers. Now, the problems what I am doing now today in this session are all from old question papers of VTU, our university only. First, I will be doing the problems on induced EMF, and then afterwards I will be doing the problems on efficiency calculations, okay, at different load conditions given the losses, or sometimes I may have to calculate the losses and calculate the efficiency like that. So, the first problem is like this: a single phase 20 kVA transformer has 1000 primary turns and 2500 secondary turns. The net cross sectional area of the core is 100 square centimeters. When the primary winding is connected to 500 volts, 50 hertz, find the maximum flux density in the core, the voltage induced in the secondary winding, and the primary and secondary full load currents. If you observe the data given in this problem, to solve this problem, I need to know about know the equation for induced EMF. If I take the primary induced EMF as E1, okay, primary induced EMF is E1, I will getting this voltage equation as 4.44 F BM AI, okay, T1, where T1 is the number of turns in the primary, okay, BM is the maximum value of the flux density, AI is the net cross sectional area of the core, and as I mentioned, E1 will be the voltage induced in the primary winding. Okay, he has not mentioned anything about the load condition on the transformer. Therefore, I consider the voltage 500 what is given in the problem as E1, 500 volts. Then in the data he has mentioned that the transformer is frequency of the voltage is 50 hertz, okay, and the transformer is rated to 20 kVA, 20 kilovolt amperes. And he has given that net area will be 10 square centimeters. Remember, in this equation the flux density will be given in Webers per meter square. Number of turns, there is no unit for that. Frequency is cycles or hertz, cycles per second or hertz. Therefore, when you substitute the area here, I need to cancel this meter square. Okay. So therefore, the area what are you are doing using here, this should be substituted in meter square, but it is given in 10 square centimeters. Okay. We need to convert that to meters. Okay. So therefore, converting this to meters, 10 divided by 100 into 100, because it is square meters, I will be getting 10 into 10 to the power of minus 4 meter square. Okay. So by using these parameters, what all is given, I can evaluate the required term, the flux density, by just substituting the values given here. 4.44, 50, Bm is unknown, 10 into 10 to the power of minus 4, it is the cross sectional area, okay, and the number of turns in the primary winding as per the data, it is 1000 amperes. All the parameters is known except the Bm, so I can evaluate the maximum value of the flux density here. Okay. Then the voltage induced in the secondary winding he asked. So I will go to the transformation ratio for the transformer. E2 is equals E2 upon E1 is equals to K. Otherwise, okay, from this I can calculate E2 is equal to K times E1. This K, it is T2 upon T1, E1. T2 we have 2500 turns, okay, 2500 turns, and T1 is 1000, E1 is 500, so I have it as 2.5 multiplied by 500, okay, 1250 volts I will get that. Otherwise, I can also use this equation, E2 is equals to 4.44 F Bm AI T2. I know all the parameters in this expression because we have evaluated the flux density here. Okay. The solution, if you see, I will be getting the flux density value, okay, maximum flux density in the value, okay, it is around somewhere around 0.2252 Webers per meter square. Okay. It is Webers per meter square, that per meter square is not there. Okay, 0.2252 Webers per meter square, or I can also write it as Tesla. It is the another unit for the flux density, Tesla. Okay. So making use of this relationship E2 upon E1 or V2 upon E1, whatever you want you can write, this is general notation is it. So therefore I will be getting a voltage of 1250 volts. So the next point what you are supposed to calculate is the primary rated current and secondary rated current. I will take the rating of the transformer as 20 kVA. I have here the relationship as 20 kVA will be, or 20 into 10 to the power of 3 volt amperes will be V1 into I1 or E1 into I1. Okay. The same thing, 20 into 10 to the power of 3 will be also equals to E2 into I2. Now the transformer, this is what the input rating of the transformer. Okay. I will not be giving the same amount of power as the input. It depends upon the power factor also. I am not considering the power factor here because the transformer is rated to volt amperes. Okay. It is always rated in volt amperes. So the primary volt amperes in the transformer will be equal to secondary volt amperes. So therefore I can write E1 I1 is equal to 20 kVA, E2 I2 is equal to 20 kVA. I know the values of E1 E2, therefore I1 will be equals to 20 into 10 to the power of 3 divided by E1 is 500. So I will be getting like this, I'll get around 40 amperes. And the secondary current rating I2 is equals to 20 into 10 to the power of 3 divided by 1250. Because the denominator is larger here, I will be getting a smaller value of the current, what I get it as 16 amperes. Okay. Now let us see here. Primary winding has a voltage of 500 volts. Secondary winding has a voltage of 1250 volts. So in a transformer, whichever winding carries larger voltage, it will carry small current. Okay. So that means the current here it is 16, and the winding which has lower voltage will carry larger current. So that is 40 amperes here. Now this difference is because to match the volt ampere rating in the transformer. Okay. Always the primary volt amperes, that is the product of voltage and current, should be equal to secondary volt amperes, that is secondary voltage multiplied by secondary current. To have this balance, whichever winding carries lower voltage carry more current, and the winding will carry larger voltage carry smaller current. Small voltage, large current, large voltage, small current. Okay. So this you have to remember. I have another problem. This problem is also based upon the EMF equation. So find the number of turns on the primary and secondary side of 440 by 230 volt, 50 hertz, single phase transformer if the net cross section, net area of cross section of the core is 30 centimeter square and the maximum flux density is 1 Weber per meter square. Okay. So it also depends on the same equation, EMF equation. So I have the two equations here, voltage induced in the secondary and voltage induced in the primary winding. Okay. So find the number of turns on the primary side. So I will be just taking the equation here. The first equation, I know what is the voltage of E1. Okay. E1, it is given as, see that I need to see the transformer rating 440 divided by 220. Okay. So the first rating will be always for the primary, the second one is for the secondary winding. Okay. So the primary winding voltage is larger, secondary winding voltage is smaller, therefore the transformer is a step down transformer. For this, if I calculate the voltage transformation ratio, I need to take this as 220 divided by 230, it is 230 divided by 440. Okay. For a step down transformer, the transformation ratio K will be less than 1. Whenever the voltage ratings are given like this, the first voltage should be for the primary, the second one will be for the secondary winding. Okay. So as per this, I have E1 is equals to 440 volts, and this E1 is given by 4.44 F Bm AI into T1. I need to calculate the primary turns T1, E1 divided by, okay, that is 440 divided by 4.44, frequency is 50 hertz in our country. Okay. So Bm, the value of the flux density, what is given as 1 Weber per meter square, and the area of cross section is 30 centimeter square. Therefore I will convert into meter square by taking the 10 to the power of minus 4. Okay. Now so definitely the ratio of these two will not give us an integer value. Okay. So if we see here, for the final value what I have given here will be, it is not an integer. Okay, I have just given an integer here. Okay, but you never get an integer here. So what you need to do is you need to round it off to the next higher integer. Okay, always the number of turns. See, I cannot have 22.5 turns. Okay, 22.5 is not possible, so I will go for 23. I will not reduce the number of turns, I will increase it to the next higher integer. So therefore definitely this T1 what you have, it will not give you a round number integer for that, so you need to round it off to the next higher integer. Okay. So he is asking for the primary turns, and I can also calculate the secondary number of turns. So for calculating the secondary number of turns, I can take this E2, equate this E2 to 230, otherwise I can say K is equals to T2 upon T1 Okay, this is equals to E2 upon E1. Therefore, T2 is equals to T1 times E2 upon E1. I know what is the value of E2 and what is the value of E1. T1 we have calculated. So, substituting in this, I will be getting that number of turns in the secondary winding. This way also we can do. It is simpler calculation compared to the direct method. Okay. The solution is provided here. So, you can go through the solution. Similarly, this is another problem where the primary winding of a transformer is connected to 240 volts 50 hertz supply. So, because the primary is connected to 240 volts, the voltage on the primary is 240. The secondary winding has 1500 turns. If the maximum value of the core flux is 0.00207 Weber, determine the secondary induced EMF, okay, number of turns in the primary and cross sectional area of the core if the flux has maximum value of 0.465 Tesla. Okay. Let us do this problem by calculating first the area of cross section for the core. We have the relationship between the flux and flux density is Bm will be equal to flux divided by area. Okay. I am taking this area, you see, I just put one suffix I, AI. Okay. This AI, it is called as net iron area. Okay. Net iron area. What is this net iron area? So, it is like this. I have my core cross section, let us say rectangular. Okay. I am making this core laminated one to minimize the eddy current losses. So, what I have here, my first lamination, okay. So, the lamination thickness will be smaller, the second lamination will be on the next side, okay, second lamination. Now, the space between the lamination what I have left, it will be filled up with a insulating material. So, generally in constructing this core or in assembling the core, I take thin sheet steel laminations, okay, provide a varnish coating on that, sorry, I provide a varnish coating and then stack the next lamination, okay. Like that means between the two laminations I always have insulation coating. Now, this insulation, it cannot carry the flux, okay. I can calculate the gross area, that is based on the physical dimensions of the core, A multiplied by B, okay, A multiplied by B. A is called the width of the core, D is called as the depth of the core. So, that based on the physical dimensions, I will be calculating an area called gross iron area, AGI, okay. I stands for iron, G stands for gross. This is equals to AB. But complete area is not made up of iron. There is a varnish coating, okay, which will not carry the magnetic flux. Therefore, to remove that area of say occupied by the varnish coating in the core of the transformer, I will be using a factor called Ki. This is called as stacking factor, okay. It is called as a stacking factor whose value we will take it generally as 0.9. That means 10% of the core area is occupied by the varnish coating, 90% of the gross area is occupied by iron. So, the relationship between AGI and AI is net area AI will be 0.9 times the gross area AGI, okay. So, this is the relationship. Now, if I divide the flux by area, net area, that is actual iron area, I will get the flux density. Now, in the problem he has given that the maximum value of the flux will be 0.465, okay. It is a flux has a maximum value of 0.465. Okay, I think there is a small mistake in this problem actually. The last one, it should be maximum value of the Tesla cannot be the unit for the flux. Okay, it should be the dimension of flux density. So let us write the maximum value of the flux density is 0.465 and the maximum core flux what you have is 0.00267. Okay, sorry, 207 it is, 207. So the ratio will give you the net iron area. Okay, so the solution I provided here. Okay, so in this the maximum flux value is 0.00207 and the flux density is 0.465. So by dividing these two, I will be getting the area like this, 44.516 meter square. Okay, 10 to the power of minus 4 meter square or 44.516 centimeter square, right. So next, coming to the secondary voltage, I will be using this voltage EMF induced voltage equation for the secondary, that is 4.44 F phi m Ts. Ts stands for the secondary number of turns. Therefore, by substituting the values what all is given here, okay, I am not considering the area because the flux value is directly given, so I can also use the product of Bm into Ai in these equations as the phi m value. I use the phi m value in these expressions to calculate the induced voltage in the secondary winding, and given the number of turns in the primary, I made use of the transformation ratio. Okay, in terms of voltages, I can calculate the primary turns. Okay, so primary turns is 523, secondary turns is given. Okay, 1500 is the secondary turns. Fine, more number of turns I will be getting more voltage, because see the primary has less number of turns, 523, therefore I have 240 volts. Here we have 689. This should be okay voltage, so I can just leave it like that. Okay, but wherever you get the number of turns, it will not be an integer. If it is integer, it is okay, otherwise I need to round it off to next higher integer. So we have a similar type of problem, so you can just follow the solution on the slide. It is about calculating the maximum value of the flux density given the cross sectional area. Okay, so this is also similar to that. So this is another problem. The required no load ratio in a single phase 50 Hertz core type transformer is 6000 by 250. Find the number of turns in each winding if the flux is to be 0.06 Webers. Okay, no load ratio he has given, so I consider this no load ratio to be the voltage ratios. Okay, so 6000 volts is the primary voltage, 250 is the secondary voltage. So I make use of these equations again. So instead of writing this Bm into Ai, I can write down the value of phi m here and phi m here. Okay, both I write phi m's. So phi m multiplied by phi m will give you the phi m in this equation. Okay, this equations can be used in calculating the number of turns. As per these equations, we have the primary voltage as 6000 volts. So 6000 is equals to 4.44 50 multiplied by the flux value is given as 0.06, T1 is unknown. Okay, so I can compute the value of T1. In the case of the second equation, 250 is equals to 4.44 into 50 multiplied by 0.06 T2. So just by dividing 250 with the product, I can calculate what is the number of turns in the secondary winding. Okay, only thing is you have to consider the given ratio as the voltage ratio for the transformer. So this is a similar type of problem, but here he has not given the cross sectional area, okay. He has given that this core has square section with a side of 20 centimeters. So when this is 20, this is also 20, because the cross section is square, 20 centimeters. So 20 by 20. So this will give you, as I told you, the gross area AGI, okay. 20 into 20, I will be getting 400 centimeter square. So this should be converted to meters. Once I will divide by 100, so 1 meter get converted to meters, 1 centimeter get converted to meters, or I can also write 400 into 10 to the power of minus 4 meter square, okay, or 0.04 meter square, okay. So this is what I have my area, gross area, but in this expression for the voltage I cannot consider the gross area because there will be a insulation layer, okay. I need to have the net area, therefore net area is always 90% of gross area, therefore I can write it as 0.9 times AGI, okay. This you have to remember. I cannot take the full value of the area, I need to consider the gross area in calculating the number of turns, okay. The problem solution is method is same, but instead of taking the flux density, flux value, I am considering the flux density now because it is given the flux density. So I need to calculate the net iron area. So this is the method what I use to calculate the net area, okay. Now from this problem onwards, that 8th problem onwards, we have the problems about calculation of efficiency on a transformer. So in this problem the transformer rating is given, okay. The rating, this will be same for the both primary and secondary winding, 50 kilovolt ampere, okay, 50 kilovolt amperes. Immediately we can write it down to 50 multiplied by 10 to the power of 3 volt amperes, okay, and it has an efficiency of 98% at full load. So efficiency is represented by symbol eta, I put a suffix FL, so it becomes efficiency at full load. So this is 98%, therefore I can write this as 0.98, okay, and at a power factor of 0.8 power factor. The second case is also given, while its efficiency is 96.9% at 25% full load. That means I write down like this, eta 25% of the full load, therefore I will put here 0.25 FL, okay. This is 96.9%, 96.9% or 0.969 I can write, okay, 96.9 or 0.969. And what is the power factor here? It is unity. The power factor is a must. Without power factor it is not possible to convert the volt amperes to watts, because the losses will be measured in watts, input will be volt amperes. So unless we know the power factor, it is not possible to calculate the efficiency, okay. Power factor is important for this kind of problems. Now if I see here efficiency eta, this will be output in watts divided by input in watts. Okay. So the output what we have here, it is 50,000 volt amperes. Okay. Now I am converting this to watts by taking the power factor 0.8. Okay. Or you can also, okay, first let me give the equation, then I will just explain each term. Then I have here 50,000 multiplied by 0.8, this is the power input to the transformer, sorry, output power for the transformer, plus the iron losses I represent it as Wi, and the copper losses I represent it as WCU. What I have taken here, this is the full load efficiency, therefore this WCU will be of full load condition. Okay, this should be of full load condition. It is not necessary to mention this. Okay, so I have here 98%, 0.98 as the efficiency under full load condition. Same lines, when I use the second efficiency, 96.9% efficiency is at under what load condition? 25% of the full load condition. Therefore, the output of the transformer will not be full load, it will be 25% of that. So 0.25 multiplied by 50,000, and at what power factor? It is at unity power factor. Therefore, multiplied by 1 divided by 0.25 into 50,000 multiplied by 1 plus iron losses plus 0.25 square full load copper losses. Yesterday while explaining the efficiency, I said the copper losses varies with the load. Okay, so when the current varies by 25%, the copper loss will vary by square of that. Okay, if the say for example, if the transformer rated current is say 10 amperes, under full load the transformer will be supplying 10 amperes of current. Under 25% of the full load, the current supplied by the transformer will be 25% of 10. Okay, 50% will be 5 amperes, so 25% will be 2.5 amperes. Because the current is decreased by 2.5 amperes, the power loss also or the copper loss also decreases. Okay, so the copper loss is decreasing by square of the percentage of the load. Okay, so in this expression I know what is the input both condition, therefore from the first equation I should calculate what is the total loss, okay, under full load condition, and in the second equation also I should calculate what is the total loss under 25% load condition. Okay, solving these two equations you will be getting the iron loss and copper loss. The iron loss, yesterday as we saw, it is a constant loss because during these loading conditions I am not altering the voltage what is given to the transformer. Okay, so therefore as the voltage is constant, the iron loss remains constant. That is why both the cases I have written it as Wi and Wi. Okay, only the copper loss will change with the load. Fine. So like this I can calculate, solving this I will be getting the iron loss and the full load copper loss for the transformer. So if I see the solution, I just wrote these equations. Okay, we have that first equation Wi plus WCU as 816.32. Don't round it off this. Okay, never do that. Okay, the second one is Wi plus 0.25 square WCU will be 399.896. Solving these two, I will be getting the iron loss as 372.135 and copper loss as 444.18. Now generally for all the transformers the iron loss will be smaller than the copper loss. Okay, now this is the full load condition, right? Only under full load condition this will happen. At any other condition the copper loss may be smaller than the iron loss, that depends on the load, but under full load always the iron loss will be smaller compared to the full load copper loss. Now in the last line of the problem we need to calculate the voltage regulation. Okay, so as per the definition the voltage regulation is no load voltage minus full load voltage divided by voltage on full load. The voltage on the full load is given in the problem as 195. So the secondary load is connected to secondary, so the voltage regulation will be always calculated on the secondary side of the transformer. So a voltage of 200, okay, this is the no load condition. You can see the voltage under full load, it is dropping just by 5 volts, okay. So from compared to 200, the 5 volts is nothing, okay. So 200 minus 195 divided by 195 will give you 2.564%, okay. So the percentage voltage drop will be, should be smaller as possible for a transformer, okay. Now this also actually depends upon the power factor, okay. As I told you in the today's definition, for a specified power factor, you have this regulation, okay. So the regulation for the transformer should be always minimum as possible to say that the transformer is a better transformer. So this kind of problems we have, okay. So this is again a problem based upon efficiency calculation. The maximum efficiency at full load unity power factor of a single phase 25 kVA 500 by 1000 volt, okay. This is a step up transformer. You can see 500 is the primary rating, 1000 is the secondary rating, so the voltage is doubled. Therefore the transformer what you have is a step up transformer, and it is working on 50 hertz and its efficiency is 98%, okay. Determine its efficiency at 75% of the load, 0.9 power factor, 50% of load, 0.8 power factor, 25% of the load, 0.6 power factor. So I have different power factors and different load condition. So I can again use the same equation, okay. That equation what we use now, I will just write like this. I take a factor x multiplied by full load volt ampere, this multiplied by power factor, okay. See, multiplication of these two, volt ampere and power factor, will give you the output in watts, okay. Full load volt ampere or full load output also you can write, divided by x times full load volt ampere, this multiplied by power factor, plus iron loss which is always constant, plus x square times full load copper loss. Given the iron loss and full load copper loss, I can calculate the efficiency. Of course the rating is also required and the power factor also to be mentioned. Given all these parameters, at any given load condition x, I can calculate the efficiency of the transformer. In this problem we have been asked to calculate efficiency at 75% of the load. So x will have a value of 0.75, 50% of the load x will have a value of 0.5, for 25% load x will have a value of 0.25, okay. The requirement for here is I need to calculate iron loss and the full load copper loss, okay. So to get that condition, he has given a efficiency for us. So the maximum efficiency at full load and unity power factor of a single phase transformer is 98%, okay. Now this maximum efficiency occurs for this particular problem at full load condition. For the efficiency to be maximum, what I need is iron loss, the variable loss should be equal to constant losses. Therefore the copper loss, which is variable loss, should be equals to iron loss. So therefore here if I substitute 0.98, okay, he said it is occurring at full load, so x will have a value of 1. Then I have the full load volt amperes as 25,000, okay, 25,000, and the efficiency is maximum at unity power factor, so this will be 1, okay. So 25,000 divided by 25,000 plus Wi plus x is 1, so full load copper loss, so Wi plus WCU, okay. If you just see the problem here, I just mentioned here for maximum efficiency copper loss is equal to core loss. So in this equation I substitute WCU is equal to WI, then try to evaluate the losses. Okay. So I will be getting full load copper loss as 251.5.1 and iron loss also equal to this. So under this condition, in this expression I substitute different values of x, okay, where the x values are represented by the first column elements and the power factor is represented by second column, and the computed efficiency what you have for the is in the third column. Okay. You can see here 0.75 load factor, which is the load is supplied at 0.9 power factor, load factor is 0.75, power factor is 0.9, efficiency is this. Okay. Like that, for a given load the efficiency do depends upon the power factor of the load. So this kind of problems, I have the remaining problems are also similar to this. Okay. Kindly go through the problems. In the next session I will be doing this domestic wiring. Okay. So that will be my last unit. Thank you.